Hi, it's Jack Jackson here. Let's take a look at some more theorems related to circles. And so here's some fundamental ones. Most of the propositions that we're going to do with circles either come down to finding some congruent triangles somewhere or maybe some similar triangles somewhere. And these first ones are going to be dealing with some congruent triangles. And I really appreciate the GeoGebra apps that Tim Brzezinski puts together. Here's one here that we're going to take a look at. Uh, and let's just go ahead and open this up in the app to make it a little bit bigger. All right, so here we have a circle. We can make it. Let's do this. Let's pull it over here and make it a little bigger. Take up a little bit more of the screen. All right. So let's just slide this and see what he's doing here. Okay, so look what we've got here. We've got a chord and a distance from that chord to the center of the circle. The distance to the center of the circle is going to be a perpendicular distance there, the shortest distance. Okay, so see those two angles are congruent, so that makes them right angles. Same way here. And these two chords, we got two chords here. They're the same distance. See? And what do we notice about the chords? If they're the same distance, they appear to be congruent chords, okay? Okay, that controls the distance. So once again, we can fix this, go around. This controls the angle here. So once again, looks like we're getting the same result no matter where we put this. Change that angle, make it over here. Same result. So that's an interesting thing. So what does this tell us? Okay, so we might get some theorems from this that if these chords are equally distant from the center, that they have to be congruent. What about the converse? If they're congruent, do they have to be equally distant? And if you draw that distance, uh, does this have anything to do with where it is on this chord? So those will be some interesting things that we might take a look at. Okay, and actually we can get a few propositions out of this. Okay, so here we go. Um, a segment joining the center of a circle to a point of a chord bisects the chord if and only if the segment is perpendicular to the chord. It's kind of related to the figure we drew, at least to one of the chords. In the plane of a circle, the perpendicular bisector of a chord contains the center of the circle. The distance from the center of a circle or sphere to a chord is the distance between the center and the midpoint of the chord. So all three of those are closely related propositions that basically have the same construction. You're just starting with slightly different givens, so your proof may be just slightly different for those, but the conclusion is basically the same. Well, you'd start with different givens and give different conclusions, but the whole situation is about the same. And then here's the part D. For a circle or for two circles of equal radii, two chords are equidistant from the center or centers if and only if the chords are congruent. And that's what we just saw in the app. So what I'd like you to do now is just pause the video and see if you can prove these on your own. It's always better when you're doing this geometry stuff, when you're watching my videos, that if I ask you to do an investigation or ask you to try to write a proof, you're going to learn a whole lot more by doing that yourself than you are just by watching the video. So I strongly encourage you to stop when I ask you to and to do certain things. In this case, I'm asking you to possibly build some of these constructions in GeoGebra and then, or maybe use the one that was up above and manipulate it, then might write out an actual proof, and um, then we can compare that to some things that are later on. And writing these proofs or attempting to write them on your own is going to be a great learning activity. Okay, so press pause and do that now. All right, well, you're back. And so let's look at a proof here. So the big thing that we're going to use here is for the first part is the perpendicular bisector theorem. We had a proof, we proved a theorem earlier that said the set of points that are equidistant from the endpoints of a line segment is equal to the set of points that makes the perpendicular bisector of that segment, that line segment. So given a line containing the center of a circle that bisects a chord, so what does that mean? It goes through the center of the circle and the midpoint of the chord. Uh, Well, both of those 2 points are equidistant from the endpoints of the chord. Well, by the perpendicular bisector theorem, the line containing the center of a circle and the midpoint of a chord has to be the perpendicular bisector of the chord, right? There's only one line through those 2 points, and since they're part of that perpendicular bisector, and the perpendicular bisector is a line, that's it. That's the line. Conversely, if you're given a perpendicular bisector of a chord, it is a set of points equidistant from both endpoints of the chord, which those are points on a circle. So it contains the center of the circle, which is equidistant from all points on the circle. That's the definition of a circle. And so it contains the circle, and that proves the parts A and B of our proposition. The perpendicular distance theorem says that the distance between a point and a line is the length of the line segment from the point perpendicular to the line. We proved that earlier. So by the previous parts A and B of this, the point on the chord where the line through the center perpendicular to the chord intersects the chord has got to be the center of the chord by the perpendicular distance theorem. The distance from the center of a circle to a chord of the circle is the distance from the center to the midpoint of the chord, and that proves part C. So now let's do the last part that was illustrated in that app that we looked at just a minute ago. Let AB be a chord of circle C and A prime B prime be a chord of circle C prime, where C prime circle is the circle congruent to circle C, meaning they have the same radius, they have the same, that distance is the same. It includes the possibility that C and C prime could be the same, so the circles would be the same in that case. Since the circles are continuous, the distance from the center point C to a point on the circle A is the distance from that center to a point B on the same circle, which is same as the distance from point C prime, the center of the second circle, to point A prime, a point on the circle, and this is the same as the distance from C prime to B prime. And let M be the midpoint of line segment AB and M prime be the midpoint of line segment A prime B prime. By the definition of midpoint, the distance from A to B is twice the distance from A to the midpoint, M, and same way for the primes. And the earlier parts of the proposition up above, we have the distance from the line segment AB to C is the distance to the midpoint, CM, and same way for the primes. These should both be primes here. And this one should be a prime as well. All right. Now suppose that we're given the chords are equidistant from the centers of the respective circles. In other words, CM is C prime M prime. Well, we know that CA is equal to C prime A prime and CM equals C prime M prime. And so the measures of the angles at CMA and C prime M prime A were both right angles. Okay. So that equals 90 degrees, or pi over 2 radians. So by the hypotenuse leg theorem, which is a special case of the big S little sa theorem. Remember, SSA was not enough to make triangles congruent by itself, but if you know that that first side is bigger than the middle side, specifically if you know it's the angle A is a right angle or obtuse angle, and you've got SSA, that's enough to make the two triangles congruent. And if if the two triangles are congruent, what does that tell you? Corresponding sides are congruent, so AM distance is the same as A prime M prime, and of course that makes AB equal to A prime B prime, those distances. So we just showed that the chords have to be the same length. And conversely, if we're given the lengths are the same, then the distance from A to the midpoints are the same. These angles are congruent, again, right angles. So it's the same thing, you just got a different leg of that triangle is congruent. So here is a GeoGebra sketch with the labeling that we just had. So here we have our chord AB. Notice that it can be any chord there, depending on what we start with. If we start with this being the midpoint and you connect it up to C, then you know that these two are congruent. Of course, that's congruent to itself. And B to M is the same as A to M. So by side, 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 these triangles are congruent. And this has to be a right angle. It's another way to look at the theorem. Another way we can look at it is if we start with this being a perpendicular here, not necessarily knowing it's the midpoint up front, we still know it's in a circle, so we know these two radial segments are congruent. This is congruent to itself. And if we know that's a right angle, then hypotenuse leg makes these two triangles congruent. Let's see. And of course, we know the distance from this chord to the center is the length of that line segment. So that kind of gets us the construction that we wanted there. And then if we want a second chord here, I put it in the same circle, but it could also be in a congruent circle, it'd be the same setup. Since it's in the same circle or a congruent circle, all of these red radial segments will have the same length. Now, if we know that they're equidistant, if you start by knowing the two purple lengths are the same, we know the distance is to the midpoint and it's a right angle. That's what we just showed. So what do we know? We know we have a right angle, we have this, and then we have these radial segments are congruent. So we have a leg and a hypotenuse and a right angle. You get four little triangles here. They're all right triangles that are congruent to each other. Among other things, or you take the big triangle here, you can work with that one too, and you're going to end up getting the blue links A prime to B prime the same length as A to B. So that shows that those are equidistant. Now, if we go the other direction, we know that this is equidistant. I mean, this is the same length. If we just start with that, and then we go to the midpoints, then we know that this distance from A prime to M prime is the same as the distance from A to M. Okay, and let's see. Well, this time we started with that, so we know the two red links are equal to the radius of the circle. Okay, and we're going straight to the midpoint. We know that's a right angle. So again, we have a hypotenuse leg. This time it's the purple leg, or no, this time it's the blue leg, not the purple one that we know. And that makes the two triangles congruent there and there. Actually makes all four of them congruent. And so now the purple links are the same as well. So depending on which way we start with this, we can eventually get to the result. So it's an if and only if statement. So if the chords are congruent, then the distances from there are measured to the center, the midpoint rather, from the center to the midpoint, and center of the circle to the midpoint of the line segment. That's the distance, and those are congruent. And conversely, if we know those distances are congruent, or distances are equal, those line segments are congruent, then the chords have to be the same length, have to be congruent as well. Okay, we have one more result I'm going to do in this particular video. Given a line that's in a plane of a circle and contains the outer endpoint of a radial segment, the line is tangent to the circle if and only if it is perpendicular to the radial segment. And then for each point of a circle, there's exactly one line tangent to the circle at that point. Let's see if we can investigate that. I'm going to actually build up the GeoGebra in real time here this time. So let's go ahead and do this just a second. I want to make a checkbox here for first chord and get rid of some of this stuff. This is B. Let's see, this is B. So I'm going to select a bunch of things here and hide them. Settings, advanced, B. Now it should be when I click that, they go away. All right, good. Okay, so we still got our center of our circle controlled by this. The radius of the circle is controlled by R here. Okay, so we got us a nice circle here. Okay. So what I want to do now is look at some tangent segments. So I want to start by just picking a point on the circle. D is fine. And I can move that around the circle. Now, what happens if we take a radial segment to here, and then we make a line perpendicular to that line through that point? Well, what we should notice is that's tangent there. Now, if it's not tangent, then there has to be, it's touching the circle in one place. If it's touching just at one place, it has to touch it too. So there'd have to be some other point. This is not going to work here, right? Because it's not actually true. But let's do this sort of by contradiction. There would have to be another point. Now, E is supposed to actually be on this line as well, right? And it would also have to be on there. Okay. Now remember what we have here. We have this angle here. It's supposed to be a right angle, right? That was the way it was constructed. Okay. But this gives us a problem. This is an isosceles triangle. This triangle DCE is isosceles, and if that's a right angle, there's another right angle, and that can't happen because now our angles are going to add up to more than pi, more than 180 degrees. So that's a contradiction. So what do we show? We show that this situation just can't happen, right? That if this is a right angle here, let's put a point out here so I can make a mark. Okay. That if this is a right angle, then this has to be tangent. And we can kind of work the other way around. If this is tangent, then it also has to be a right angle. Again, we're going to kind of do this by contradiction. So if it's not a right angle, see, so again, what are we trying to do? We're trying to say start with a tangent line, then show it's a right angle. We did it the other way around just a minute ago. So we're looking at somewhere there's a place where there's a right angle. Let's pretend it's at E. Okay, which clearly it's not, because this is not going to be able to be something that we can actually do. It's a proof by contradiction. Okay, but let's pretend that guy right there, this one at E, is a right angle. Okay. Well, now what can we say? Well, the shortest distance, the closest distance to a line is uh, is the place where we have a right angle. We proved that earlier. And so um, this is a problem because if this is a tangent line, every point that's not that one point that where it's tangent is in the exterior of the circle. And so this line segment has to be longer than this one, but that's not possible if that one's a right angle, because then this angle here would have to be bigger than that angle. And if that's a right angle and this one's even bigger, that doesn't work. The triangle's not going to work out. So we proved then that if uh, that a tangent line will have a radial segment from the point of tangency to the center, that will be it will be perpendicular, right? That's how you go about producing a tangent line to a circle here in GeoGebra, is use that fact. And so we did it as an if and only if. If it's a perpendicular to a point there, to a radial end of a radial segment, it has to be tangent line. If it's a tangent line, it has to be perpendicular there. This is if and only if. Now, that means that if you take any point here, no matter where I put the point D on the circle, no matter how small or how big the circle is, and no matter where you are on the circle, that there's only going to be one tangent line there because there's only one perpendicular to this line segment through that point. All right, so there's some basic results about equidistant chords and tangent lines.